Whenever you all are ready, can you talk through what you put together?
Yeah, so good morning. My name is Nathan.
I'm Natalia.
And I'm Daria.
And together we made a really nifty baseball game.
Okay.
So it's all operated through this box, which you have to operate kind of gingerly because the breadboard is inside of the box.
Uh-huh.
But this is the button that you use to toggle the game as well as initiate swings, and this is the joystick that you use to move your bat up and down to try and hit the ball.
Cool.
So I'll try and say this is a very difficult game, so forgive me if I don't actually hit the ball. But as you can see in the bottom left, there's like a power
Yeah.
bar. Nat, can you help me with this? I have to go nonverbal so I can hit this ball.
Yeah. So when you hold the power bar, it goes all the way up, but then as like a punishment, when you hit
Ooh.
the top. Oh wow, yeah.
And you can see on the top right, there's like an active ball distance. So now that you've seen one ball hit, I can show you something cool. I'll wait for this to cycle through. If I hold the power all the way, it goes up and then back down to kind of penalize just smashing the button. So it's an act of both timing and precision with the joystick.
Cool.
If you'd like, now that you've seen a little bit of a demo of what the game looks like, do you have any specific questions, or should I just...
Nathan, I feel like we should mention that like with the timing also comes like how a typical bat swing operates. So you swing early.
Uh-huh.
Oh my god, I always get this wrong. You swing early, it goes left. You swing late, it goes right.
Yes,
Uh-huh.
And
correct.
so when it goes straight, it's like really impressive, like what Nathan just did. Because I have yet to hit the ball once on this game.
And you're doing a full perspective.
Yeah.
You fake the perspective, but it's good. It's a good fake perspective.
Daria, can you talk about
Or is it
that?
fully 3D?
Yeah, the perspective, we
Weird
changed
foul
the
ball.
map so that it's no longer like a fake perspective. So we have a function where if you input a point in three-dimensional space, it converts it to a point on the VGA
So
screen.
it's real
It's real.
perspective.
Yeah.
Wow.
Yeah, so every object has a real life XYZ coordinate that gets translated into VGA XY coordinates.
Yeah.
So for example, the ball, as it's flying, has a real life XYZ coordinate that's updated based on a predetermined pitch trajectory and then a kind of physics defined trajectory off the bat.
Very nice. Yeah, the perspective looks great.
Thank you.
It's
It took a lot of
extremely
trial and error.
three-dimensional. Is that a foul ball?
Yeah. No, it'll come back down. It's just, I hit it real far.
Yeah.
I mean, in reality, that'd probably be a fly out, but hey, I'm not keeping score. So, I mean, like, the ball's
Very
fast.
nice.
So you can see, not impossible to hit the ball,
But challenging.
quite as a
Grounder.
Of course, with any project, there's stuff you wish you could have done better. Ground balls would have been cool to animate, but introduced quite a difficult layer of complexity.
Uh-huh.
Because modeling rolling, modeling how much friction you want the grass to have is I think, non-trivial. If you'd like, would you like us to talk about either the pitching, batting, or anything else?
Sure.
I feel like we should show the demos. Is that like available?
Yeah, if you guys are interested. So if we want to talk about pitching, the way that we modeled pitching is through a function that we created in Desmos. So as you can see, there's a number of parameters that change what a pitch might look like. So A, obviously, is amplitude. Let me pause all these. H is the height at the batter's box.
Uh-huh.
N is where the maximum amplitude is going to happen. D is where you want the endpoint to be. So for us, that's a constant. It's always, the distance from the mound to the plate. And then G is initial release height. So for every pitch, we generate a number of random parameters that are passed into both the ball's X and Y, velocity functions.
So cool. So this family of curves fully parametrizes all your possible pitches.
Exactly. So whenever we reinitialize a pitch, all that needs to be done is creating a number of random parameters. So
Neat.
instead of physics defined, this is a more algorithmically defined trajectory.
Sure.
And we did that because modeling ball spin and its interaction with drag and all of these other forces is extremely, extremely, extremely complex. Maybe if we were doing this for a PhD, we might try and implement that. But for the bounds of this project, we thought that this was a good abstraction.
Yeah.
How does this actually work? So every time we reanimate a frame, that moves a time step in time. So all that we really have to do is pass into our trajectory function the pitch's individual parameters and then the time step. And so then that spits out a real life XYZ coordinate that we then animate using our animation function.
Where did the function come from? Did you
So,
make it up?
oh yeah, we developed this with a lot of help from one of the TAs, Mahmood.
Cool.
So he was very, very helpful in helping us to get this up.
It's really nice. It's a
Thank you.
really effective game. The perspective is just really compelling.
Oh, we do,
Oh,
yeah.
yes,
Oh, there's
play
music.
it. I forgot about that. Yeah.
Don't you feel like you're right in the atmosphere? Crack.
Yeah.
So music we implemented a little differently than what we did in class. Instead of doing DMA determined music, we actually used PWM. The reason that we did that is because the song obviously is quite complex, and I think would be more difficult in individually modeling the signals given through the DAC to the speaker,
Yeah.
rather than using a GitHub library that we found that takes in an MP3, creates a WAV file, and then converts that WAV file into PWM signals to send to the.
So you're driving those speakers from a PWM?
Yes.
Yeah.
Wow, that sounds really nice.
Thank you.
Okay.
And it was pretty easy to do.
Okay.
Yeah.
Okay.
So if you're curious, this is what our actual. This is the WAV data.
Yeah.
So this one by one gets sent using PWM to the speakers. So you can see it's 124 for a while, and then you begin to have some
So each
unique
of
values.
these is a byte, right? And so the total size of your song is
Huge.
what
Sorry,
was the
I was
size of
just
the
happy
array?
with that. So it's about 100,000 samples, I think.
100 kilobytes or so. Okay. Wow.
So
Sample rate?
the sample rate I think is determined by
It's a
some
bit.
parameter.
Oh, it
Yeah.
says
Do you
right up
remember?
there, unless that.
It's at 8.
Okay, so that's like 12 seconds.
Oh yeah, more or less. So you could see, unfortunately, it does clip and then reset quite frequently,
Yeah.
and that was a memory limitation. So I'm sure if instead of storing the entire array in memory, and if instead we could have algorithmically determined it, we could have had a whole song.
Sure.
But
Yeah.
but every decision has trade-offs.
Yeah.
Is that a constant array?
Yeah, it is a constant array. So this is created by a Python file that we found online, from MP3 to WAV, and then
Okay.
from WAV to this array of values.
It's a good utility to have.
Yeah, it was pretty useful.
Really, really nice.
If you'd like, we can talk about how batting works.
Sure.
So the way that we implemented batting is we have a button and a joystick. The joystick moves the bat up and down, and the way that we do that is every single frame, we read the analog value coming from the joystick's pin. We do some transformation on it, and then convert it to a power between 0 and 1. Oh, sorry, I got a little bit confused. We're polling this joystick's value, and then transforming it to some value in between this range, and then just animating it at that range. A small quirk to make the game a little bit easier is that the bat within the game's logic is 10 centimeters wide. Obviously, that's way larger than any real life bat, but just makes it a lot easier to hit the ball.
Sure.
But we're still animating it at a 1 pixel width to make it look a little bit more realistic.
Cool.
As for the power mechanics, we have 2 interrupts tied to the same GPIO pin, one on the rising and falling edge. And essentially what that does is start and then stop a timer, as well as set a Boolean to say, okay, we have swung. Once you have both the timing and the position parameters, that's passed into an actual batting function that then determines, did we miss either through position or timing? And if neither of those are the case, you actually hit the ball, at which point you calculate the polar coordinates, or sorry, spherical coordinates of where the ball's going to go. So you have the angle left and right, you have the angle up and down, and then you have the velocity, which is essentially the magnitude of your vector.
Awesome.
Yeah, and then finally we translate that into a Vx, Vy, Vz, which is then animated using physics. So constant Vx, Vz, a varying Vy with gravity.
Yeah.
Which gives you this beautiful like parabolic trajectory. If I'm lucky enough to hit a ball. Lucky or skilled, they're like two sides of the same coin.
Will it pitch? Does it only pitch strikes, or will it also throw balls?
It does
No,
throw
it
balls.
throws balls, yeah.
Okay. Oh yeah, I see
Yeah, we
that.
actually just got a ball.
There's another one. Okay, gotcha.
Yeah. The way that we check for this is if you swing the ball and if you swing the bat and you miss, every single time it counts as a strike, which makes sense. If you did not swing and it passes the batter's box, essentially the Z equals 0 point, we check the X and Y position of the ball and see if that's within the strike zone.
Sure. Really cool. Awesome.
Very nice.
Thank you all. That's a really excellent demo.
Thank you.